Okay, so okay, so let's try to apply our learning of thrust to do something more, right? So what we are going to do here is that allocate 3 device vectors, let's say x, y, z, with 10 elements, right? So that is just a device vector with x10, y10, as well as z10. And I want to initialize x to 0, 1, 2, 3, so that we know can be done using a sequence command. So thrust : sequence x dot begin to x dot end, right? And then I'm going to compute y equal to minus x. So there are multiple ways in which this can be done, but one of the ways is that we can use a transform function which goes from x dot begin to x dot end and writes at y dot begin, right? So it's a unary operator, right? So transform has two variants. One is the unary, one for the unary variant, another for the binary operation. In this case, it's a unary operator negate, which is provided in thus, which can be applied to every element from x dot begin to x dot end and return back to y dot begin, right? Starting from y dot begin. So that is one transform. The other one will require us a second parameter, right? So for example, if there is a binary operator, then we'll require x dot begin to x dot end, like we had dsrc dot begin to dsrc dot end, and then dsrc2, right? Before we gave ddst, right? So y in this case is ddst. I can use a fill function to fill z with 2 and then compute y equal to x mod 2, right? So this we are doing. So there is a I should say that there is a sequence of operations that are happening. Finally, what I want to compute is something. So here is the binary variant, right? So from x dot begin to x dot end and using z dot begin to probably z dot end, I want to write something at y dot begin, starting from y dot begin. And what is that? I want to use a mod, which means that x mod z is what is going to happen. And that's the reason why we initialize z with 2, right? Filled with 2 values. And essentially what this is going to give you is y equal to x mod z, right? So that is, these are the operations that we need to kind of think about and then split it using various thrust functions. I want to replace all the ones in y with tens. That is a simple replace function, 1 by 10. And I can print y in a different way also, like you can do a for loop, but there are other ways. For example, you can use copy to the cout stream, right, with delimiter as new line. And that is also going to copy from y dot begin to y dot end onto the stream. Or you can use a for loop. Okay, so that seems fine. Any questions, please ask. Okay, so let's come to the user-defined functors, right? So functors essentially means that these are function objects. And I'll just quickly show how that gets done in C++, and the same concept we apply here. What we want to do is we take this specific example of computing the a into x of I plus y of I operation, where a is a constant and x of I and y of I are different vectors. And we usually compute result of I equal to that. Finally, we also do a summation over result of I. That is one possibility. And therefore, this is called as summation of ax plus y, right? So saxpy, saxpy is the operation that we usually call this as. So let's say that you are given this xy and result, and we have populated xy appropriately. And I'm going to now call a transform, right? Because I want to transform result with the values from x and y. So I'm going to give that as parameter for all x dot begin to x dot end and y dot begin to as many elements. Write to result, write starting from result dot begin, an operation which is done like this. Right? So this is my operator, which is not defined inside thrust or STL. This is something which I am defining. How do I define that? As a functor. And we define functors using a structure, right, or a class. So I'm going to write that structure whose name is going to be saxpy, right? So this is going to create a temporary variable of that name whose parameter is a. What does that mean? That means that I need to have a as a parameter to the constructor of saxpy. Constructor meaning a function which gets called automatically whenever we declare a variable of that type. So we'll define that constructor in this space, but let's look at the operation, right? So the another aspect of functor is that it automatically calls a function operator, right? So in C++, all these operators could be overloaded, right? So in a similar manner, we are going to overload this. You might find this a strange syntax because there is a parenthesis and then there is another parenthesis. But like you can do x plus y on vectors or x plus y on any arbitrary class. In a similar manner, you can have, so this could have been then plus, right, this particular operator. So this is an operator which we are overloading. We are saying that I am going to give it a new functionality for this XP type. So what does it do? It takes two floating point values, which is going to be coming from x and y. So I'm just calling it as x and y. Right? And these need to be passed by reference. So keep that aside if you are unaware of pass by reference. And it is going to return a new value, which is going to be some computation of x and y values. Okay. So for every pair of values coming from x vector and y vector, I'm going to do some computation which is specified here. And that return value, then the transform function takes care of writing into result. Okay. So what is this underscore a? This underscore a, according to our formula, needs to be the same a as is specified. But then why am I marking it as underscore a? Is underscore a something interesting with respect to a? No, it's a separate variable. But I want it to be accessible within each invocation of this local function, which we are calling is a operator, function operator. So that need to make that available, I am going to make use of the constructor and store it as a local variable. So this saxpy in the case of C++, the constructor has the same name as the structure. And then I pass this int a as a parameter from here. And that I am going to store, right? So this particular syntax that I'm specifying here is same as saying underscore a equal to a. So that is in the parenthesis, in the braces. And then I declare that as a constant float, which can be initialized in the constructor, although it is a constant. Okay, so this is all gimmick that we need to do to ensure that this particular functor can be applied on every pair of elements coming from these two vectors x and y, and write it into the result. So, but once we do that, then that can be utilized. And by marking it as host vector, essentially this functor can be called from either CPU or GPU. And how do you know it is called from CPU or GPU? That is decided by whether x and y are host vectors or device vectors. All right. Any questions on this part, on the CUDA side of it or the C++ side of it? Those of you who have not studied C++, you might have to spend some time understanding this syntax. But those of you who are aware, hopefully you will be able to get this part quickly. All right, I don't see any questions. That's not a good sign. Okay, nevertheless, I'll have to move ahead. But if there are any questions, feel free to ask me later. Okay, so I'll leave this as a homework exercise. So essentially, we want some vector to be x on host, y on device, fill function to be used, fill function to be, or sequence function to be used here. And then I want to have a binary operator minus and a multiplication operator to be defined for element wise minus and element wise multiplication. Did anybody have any question? I was on the slide. Okay, if not, we'll move ahead from here, right? So thrust reductions, right? So yesterday we discussed reduction briefly, and we said that it needs to be power of 2. We need to implement a barrier, right? If it is a thread block, it should be sync threads. If it is across threads, then it should be across GPU, then it should be global barrier, etc. All of that is taken care of using thrust reduce function. So you just have thrust reduce, you specify the range, and by default it takes care of the plus operator, right? You can also specify a particular operation, because we said that any associative operator can be cast as a reduction. So that can also be done. You just specify that as a functor and some initial value, right? And essentially that will take care of computing the reduction. And you can do min, max, everything using all these functions. Or if there is more complex processing that your application demands, that can be implemented using a functor. Okay. Okay, so let's do this particular classwork, right? So let's say we want to implement a count functionality using reduction. So what that means is I want to find the number of occurrences of some element inside, let's say, a host vector or a device vector. And for that, I should be able to do. Okay, so I'll leave it at this, right? So I would like this to be implemented as a reduction. Is it an associative operation? Yes, it is an associative operation. It doesn't matter whether you count to the left side first or the right side first, you will get the same counter. And I would like you to implement it in this manner, where essentially you will have to implement this part. So this is again going to be some functor similar to saxpy that we had. In this case, you might call it, let's say, count of something, right? So where that something is the element that I want to count. Let's say count of 5, which means that tell me number of occurrences of this 5. I would like you to spend some time thinking about, or even writing, how you will implement this. If you want, I can possibly keep it here. So using such a syntax, just that we'll not use transform, we'll probably use reduce. But let's see if you are able to think on these lines. And if you have any questions, please feel free to. Okay, we have to use saxpy or subroutine as subroutine. I mean, not saxpy. You'll have to implement it as a separate functor like count. Because the functionality is different, right? So I want to count the number of occurrences of a particular element. So essentially, you will have count of A, right? So that is what will be the functor.
So can we have another? I mean, I'm just thinking in terms of approach. So I have an array which has frequencies of different numbers, right? And I want to calculate the frequency of each number, right? So I take another array of length of the minimum and maximum of the values that are in the earlier array, and for each value that I access, I go to that index and increment to 1.
So that is one possibility, but I will also say that we are overdoing something. So if we want to find out the occurrences of one number, we are finding out occurrences of all the numbers.
Okay, we want just one number. Okay.
I mean, that we are giving as a parameter. So if we can do it, that will be helpful. I mean, efficient. Yeah. Okay, let's see how that can be at least called, right? So I want to use thrust reduce on a vector initialized to 0 and my count of, let's say, 5. Right? So this is what I would like you to implement. Yeah, sure. So what Sandeep is asking is, what does transform do and what does reduce do? Reduce is a special transform. And so transform, as we said, is a mother of all various transformations, where you can say that I want to apply some functionality onto as a binary operator or a unary operator onto a sequence of elements. That sequence of elements is specified using those iterators, begin and end. Whereas reduce is a specific transformation, which is only going to apply some functionality across all the elements and reduce all these values to a single element. Right? In this case, for example, I want to apply that my count onto all the vector elements and compute that value, a single value. Even the minimum, maximum, addition, all of these we said that can be cast as reductions. So think about reduce as a specific transform. Oh, I missed one question. Okay, Chinmay has given an answer. Yeah, we'll have to. Yeah, so your approach is correct, Chinmay. There is a small part that we'll have to worry about, that where you define that count. I mean, connecting that actual count with the functor is also one thing that we will have to do. But otherwise, what you are writing is on the right lines. Okay, so let's write that. So my count is a functor, and its constructor needs to have this 5 as an argument, so it should be an integer, which I am storing into a local variable. So that is this part. Okay, so that takes care of the initialization. In the operator, right, the function operator that we have specified, which is host device, it returns an integer, which is the next count. Okay, and it takes two parameters. Where are these two parameters coming into picture, right? Because we said that it is a unary operator in a sense, right? So it is operating only on the vector. But the reason why it gets two parameters is the first parameter tells whatever is computed so far. And the next parameter says whatever is the next element. Okay. So y is the element of the vector and x is the previous count. Therefore, so this, by the way, this is not something which we are deciding. This is decided by reduce. So if y, the element, is same as the one that we are looking for, then I increment that count. Otherwise, I keep the count as it is. I return that count. So that is going to give you an implementation of this my count. So please think about it later. And yes, Chinmay has a question. In reduce, do we directly add all the return values? Sorry, I didn't get that. What do you mean by all the return values?
Hello, am I audible?
Yeah, Chinmay, go ahead.
Yeah, actually that x plus 1, okay. So there, how do I put this? So this x is currently having the count, right? Return y is equal to underscore a, then x plus 1 or x. Okay. So I was thinking that this should be, this is 1 or 0. So that is why I thought, I think we are directly adding it. So then what about the like consistency of this thing? Like what I'm expecting is my count would be executed in parallel somehow, right? So then how does this manage the x values managed?
That's right. So yeah, so that's an important question, right? So yesterday when we said that the reduction, the way we implemented was with different parallel chunks, right? So two elements added together, another two elements added together, and so on. And all of this was happening in parallel. Whereas this one seems to be doing something slightly different. It seems to be almost sequential, right? So we have faced this trouble earlier, and some of our students have digged into this, and they have said that this actually, the way it gets implemented seems to be sequential, right? Which means that at least for our functors, I don't know if it does similar things for the internal implementations of some, etc. But at least our functors get implemented exactly in a similar manner, and that can be checked by printing the values of x and y in every operator that comes in. So which means that if your array consists of, let's say, 1 2 3 4 5 5 5, it will call with 1 5 first. Sorry, it will call with 0 1 first, right, where 0 is the original count and 1 as the element. It will call with 0 2 0 3 0 4 0 5, and then 1 5 and 2 5. Right? So there seems to be some sequentiality here. So this is not exactly how the reduction that we saw yesterday was working. That had better parallelism. This doesn't seem to have, at least for user-defined functions.
Okay, sir.
Sure. Any other questions here? All right. So so there is a, yeah, so we did not discuss prefix sum, so I'll probably skip this part. Okay, let's come to the second topic, which is going to be related to streams and events. So far we have been saying that yes, you can invoke these different operations, different kernels in parallel, but we had a single queue, and therefore everything was getting scheduled there. So everything was sequentialized. Now we are going to make it parallel, and that is essentially going to streams. So asynchronous processing is what is required, which means essentially concurrent processing. So what all can become concurrent? So the computation that is happening on the host with respect to what is happening on the device, CPU to GPU memory transfer, and GPU to CPU memory transfer, right? As well as GPU to GPU memory transfer on the same device, and GPU to GPU memory transfer across devices. All of these 6 different parts can simultaneously be concurrent, can simultaneously be active. And that is the amount of parallelism that you can get when you have a multi-GPU system, right? So the last 2 parts will not come into picture when you are the last 1 part will, the 6th point will not be applicable to multi-GPU, but otherwise this is going to be applicable. Sorry, the 6th point will be applicable only for multi-GPU, whereas the first 5 are also applicable to a single GPU system. And we would like to exploit this parallelism further, because for large programs and where time is critical, we would like to parallelize as much as possible. So all of these need to be taken care of. So let's try to do that. So this is our original program, right? So we have 2 kernels, K1 and K2. Both are invoked with some number of threads, and they do some processing and print K1 and K2. This whole thing is completely sequential with respect to K1 and K2, which means that all the K1s precede, that is this particular output, precede all the K2 outputs, right? So I hope this you are agreeing with me. Now, to specify the stream to ensure that K1 and K2 become parallel, we will use the 4th parameter of our kernel launch, right? So the 3rd parameter of kernel launch was the dynamic shared memory. Now we are going to use the fourth one. So I specify the dynamic shared memory to be 0. And I specify two parameters, S1 and S2, which are going to tell me the streams or the work queues in which this kernel should run or should go in. How do I declare those streams? CUDA stream underscore type. So I use CUDA stream create to create those streams, and that's it. After that, I start using these. And that can give you an output where K1 and K2 could be in arbitrary order. Is it possible that K1 and K2 are intermixed? Yes, that is also possible. Right? Depending upon how the implementation is. Usually it doesn't, you might not see it unless you run it for a very large input, or even for large input, you might not see this intermixed output, but we should not rely on it. What that means is that only because the outputs are K1 followed by K2 or K2 followed by K1, doesn't mean that there is no intermixing. There is intermixing happening. That means that if there are instructions from kernel 1 and instructions from kernel 2 executing simultaneously and operating on the same global memory, it's possible that one kernel's effect will be visible to the other kernels. So that we should be aware of. The reason why you might not get always the interleaved K1, K2 is just an implementation of printf, right? So therefore, maybe it is concatenating all of the input and then concatenating all of the input of the other one. And therefore, you might not see an interleave. But there is an interleaving happening. Now the kernels are running parallel. Okay. So streams allow us to do this. So what is a stream? It's a queue of device work. The host enqueues the work typically, right? But as we said, that you can call a kernel also from a kernel. Therefore, device can also enqueue the work and returns immediately, right? So that's what we were discussing, that there is synchronous kernel invocation, that is pushing it into the queue is synchronous part. The CPU is waiting till then. But once it is enqueued, then the CPU doesn't wait. CPU goes ahead. So the device schedules the work from streams when resources are available. Various CUDA operations like kernel calls, mem copies are part of the stream. Operations within a stream are always ordered and they cannot overlap, whereas the operations across streams are unordered and can overlap. I hope this just summarizes whatever we have discussed so far. So let's do that, right? So we want to write a code to overlap two data transfers. So there is some CUDA mem copy happening. You can decide the direction and type and variables, etc. And I would like you to think about how you will overlap two data transfers. And if there is any question, please ask. And the reason you should ask a question is because we have not really discussed CUDA mem copy with a stream, right? We just discussed kernel call with a stream. Okay, so we can also write a code to overlap data transfer with kernel execution, right? So that is also possible, as we discussed that those 5 points are possible. So let me generalize this. So what I'm going to do is that there is some large amount of data available, right? And one possibility of doing it is pipelined execution, where I say that I'm going to split this large portion into multiple pieces, and these pieces I'm going to operate on one by one. Right? Thankfully, these pieces are parallel in the sense that they are not interdependent. And therefore, I might be able to do everything in parallel. That is one possibility. But then operating on these data items, so I'll have to increase the number of threads with which I'm launching the kernel, but maybe that number is too large. Right? Each piece is still large enough. So another possibility is that maybe I can launch different kernels for each of them. But if I launch different kernels for these different parts, then I need to ensure that data that is required is copied before that part starts execution, as well as when the the result is available, I'm going to copy back the result at appropriate time. Right? So there is some sort of a dependence between data in the GPU computation and then data out. This sequential flow needs to be maintained for each piece of data. But across pieces of data, this is all parallel. Right? So that is what I take advantage of in creating my streams, where I say that there are going to be multiple streams available, right? And I am going to use a function called CUDA memcopy async, where we said that by default CUDA memcopy is synchronous with the CPU. Here I am just going to do an asynchronous execution. Why? Because I want to launch this across streams. How many streams I have? I have n streams. So I have divided the data into n different parts. What does it do? It's going to copy in from host HPTR to device PTR. Ignore that I part, that is just specifying the index, which is indexed by, the chunk n bytes per stream. So host to device happens in a particular stream I. Where I have a declared stream I, that is declared a priori. So there is an array of CUDA stream underscore T, and all of those are, let's say, CUDA stream create of ampersand stream of I is already done. So I push the first copying in meaning copying into the GPU in stream 0. I push the kernel, which is it's the same processing kernel, into the same stream such that it is going to operate on that particular in PTR that I have copied. So only that much data it's going to process. And the output is going to be written at D output PTR at a particular index. Right? So similar to the input being split, there is output also being split, and that is getting generated by different kernel invocations. Once that gets ready, the output, I'm going to copy back the output from GPU to CPU. Okay, and this I go on repeating. So what this is ensuring is that there are actually 3n number of GPU operations we are doing. 2 times n as CUDA mem copies and 1 times n of the kernel K launch. The in, kernel and the out, these 3 are sequentialized into each stream, right? So there is a sequential dependence across these for the same I, but across I everything is parallel. So depending upon, so I'm going to launch it with large number of streams. Maybe those many streams are, that much parallelism also doesn't exist in the GPU. But I'm going to launch it as I want and let the CUDA handle the amount of parallelism that is available. So this is going to ensure that our data transfers across different I's are overlapped whenever possible, and the kernel launch or the kernel execution is also overlapped across I's. So any questions on this particular part? Yeah, Sandeep.
Sir, are we working on the same array, I guess, because this dout pointer and dean pointer, when you are calling to the kernel, I think we are working on the same array, right?
Yes, the input array and the output array both are the same, just that we are splitting it into different parts, chunk many parts, where chunk size is n bytes per stream.
Okay, sir.
Yeah. And one question I have at this stage is that what if I use CUDA mem copy instead of CUDA mem copy async? What happens, right? So I would like you to think about that until I take Sayan's question. Can you explain the syntax once more? Sure. The syntax of CUDA mem copy is there is a destination address, then there is a source address, number of bytes to be copied, direction of the copy, and the string. Right? So CUDA mem copy also has this syntax. CUDA mem copy, CUDA mem copy Yeah, so that is fine. So stream of I, that specifies in which stream this particular operation goes. So as far as kernel call is concerned, it has 4 parameters: the number of blocks, number of threads per block, amount of dynamic shared memory, and the stream. So I'm ensuring that there is a dependence because of this stream across these 3 operations: copying in, kernel execution, and the copying out. So is there any specific syntax that you wanted me to focus on? There are some parameters that we are passing to the kernel, which is the input pointer, output pointer, and the number of bytes per stream. So says we can decide on which stream we want to do the transfer on. Yes. It is totally up to us to decide on which stream we schedule these different operations. So if we push, for example, let's say I equal to 0, CUDA mem copy we do in stream 0. I equal to 0 K we push to stream 1, and I equal to 0 this last part CUDA mem copy we push to stream 2. That means that 0, 1, 2 streams are containing these 3 operations for the same I. Then we are going to be in trouble, because copying in might not be over by the time kernel begins, and copying out might begin before the kernel finishes, before the actual result is available. If we schedule 2 transfers on the same stream, won't they be queued and happen one after the other? Why will overlap happen? You are right. So there is a stream of I in which the scheduling is happening. And how many such streams exist? There are n such streams. So the parallelism is across streams. So there are n chunks which are getting processed in parallel. But as far as one I is concerned, that is sequential. Does that seem reasonable, Sowmeya, or am I missing something in your question? Yes, the overlap is only across streams, right? So let me just emphasize that part. Where did I mention that? So operations within a stream are ordered and cannot overlap, whereas the operations across streams are overlap. So one stream is like one sequential flow. Right? It's a queue. So all the work within that is sequential. Okay. Abhishek says cudamalloc does not affect the correctness. I didn't understand that.
The sense that what we are trying to do here is that we are trying to divide the input data by copying it via different streams and operating on the copy data via some kernel call for that stream, right?
Okay.
So since the only difference between CUDA mem copy and CUDA mem copy async is the explicit implicit synchronization. That is, I mean, the control flow synchronization.
Correct.
So enforcing the control flow synchronization won't affect like the expected kernel computation is what I wanted to say.
Correct, correct. Yeah, so you are saying that CUDA mem copy does not affect the correctness. Yes, that is correct. That is correct. So the CUDA mem copy, if we use instead of CUDA mem copy async, the correctness is the same.
Was that if we use async as well, so in order for your kernel to begin computation, the copy has to be completed, right? So the turnaround time for the computation won't be same irrespective of whether it is CUDA copy or CUDA mem copy async.
Yeah, so there is something interesting with respect to that, and I'll come to Abhishek's question. Right? So what is this difference between CUDA mem copy and CUDA mem copy async, which is playing a role here? Is there any difference between these two? So think about it this way, right? So since we are pushing this CUDA mem copy or CUDA mem copy async into the same stream for a particular I value, right? So until this CUDA mem copy async is over or CUDA mem copy is over, the kernel cannot begin execution. And until the kernel is over, the reverse CUDA mem copy or CUDA mem copy async cannot begin execution. Right? So this should be understood that correctness wise there is no problem. Now let me take up some suggestions. Is stream is really required in CUDA memcopy? Yes, it will be. I mean, we'll specify that as part of CUDA memcopy also. I'm just saying that CUDA memcopy async and CUDA memcopy syntax remains the same, but the because of using CUDA memcopy versus CUDA memcopy async, what is the behavioral difference that you get? Chinmay says CUDA memcopy is blocking. It waits till we transfer all the data, so we won't move to the next CUDA memcopy. That is correct. And Sandeep says that there is no parallelism if CUDA memcopy is used. That is also correct. Right. So think about it this way. CUDA memcopy async, it doesn't mean that, I mean, it's asynchronous, but it's asynchronous with respect to the CPU. All of this is going to work, this particular code, if this CUDA memcopy async is invoked by the CPU and the CPU processes the next iteration. Then only all these operations are going to be actually running in parallel. If we replace one of these CUDA memcopies with CUDA memcopy asyncs with CUDA memcopy, which is synchronous with the CPU, then the CPU is going to wait till that CUDA memcopy is over. Currently, it is not waiting. So it will invoke all these 3 into n number of operations and start executing the next instruction after the for loop. But with CUDA memcopy, each CUDA memcopy is blocking, and therefore each iteration will get blocked. And if each iteration gets blocked until one iteration is over in one stream, the second iteration in the second stream will not begin at all, and therefore there is actually no parallelism. And therefore, while exploiting this parallelism between CPU and GPU or across these various functions, it's very important to remember that you should use CUDA memcopy async rather than CUDA memcopy. Okay, good. So I'll probably leave this. Okay, maybe we'll quickly discuss this part, right? So what are the difficult? Yeah, Abhishek, go ahead.
So to clarify, so what you mean is that if I use CUDA memcopy, you are versus CUDA memcopy async, you are only trying to expedite the host code in the sense like you're making that part of the code faster. That also means that if you use CUDA memcopy, there might be a chance that it might consider an IO and the process might get context switched. So you are trying to avoid that part by using async. Is that the difference, sir?
No, not like this, right? So think about it this way: that you have, let's say, you have thousands of notebooks in your room, right? And there is a truck which is waiting outside your hostel room, such that you want to transfer all those books to your home, right? So just give me 1 minute. All right. So let's say that we want to transfer all these books from your hostel to your, let's say, native place. Right? So you can carry only maybe a few books, right, in your hand. So you are going from hostel room all the way to this truck, which is standing outside your hostel, and then keeping it there. Right? Now, during this time, while you are keeping it at the, let's say, the entry of the truck, the person who is going to take this is going to take these books and arrange those appropriately within the lobby of the truck. While that person is arranging these books, you are not going to wait there, right? So you are going to go back and fetch the next set of books so that this pipeline is continuing, right? So you are doing it asynchronously with respect to that person, but that person cannot begin the rearrangement of books until you have brought that particular set of books for the next round, right? So within an iteration, that is within a set of books, there is a sequentiality between you bringing the books and the person arranging those books. That is asynchronous processing. So that is what CUDA memcopy async is going to achieve, that the data is being brought into the GPU, the kernel is going to get invoked, as well as the CUDA memcopy is going to happen, but all of these are being pushed into the same stream, and therefore these are going to happen one after the other. But as far as arrangement of books by that lorry person and you for the next set of books is concerned, these can happen in parallel. In a similar manner, when the GPU is processing iteration I, that is CUDA kernel in a particular iteration, at that time the CPU should move ahead and start processing or start launching the CUDA memcopy for the next iteration, right? So that is what async is going to do with respect to the CPU. As far as the GPU is concerned, it is all synchronous in the sense that CUDA memcopy and CUDA memcopy async, the behavior is same with respect to the GPU. It's the CPU which is going to differ. And because the CPU is blocking, that is, if you are waiting at for the person to rearrange the books and then go back and fetch the next set of books, then that is going to take more time, which means that your fetching of the books from your room and the arrangement of the books in the lorry, these are not parallel. I mean, across iterations, there is no parallelism. So that is what CUDA memcopy is going to do. That CUDA memcopy means that the CPU is going to just wait there. CPU so let's go step by step for iteration I equal to 0. Right? For I equal to 0, CPU does CUDA memcopy async, pushes it into a stream 0. Then it pushes K into stream 0. And then it pushes another memcopy in stream 0. At this stage, this is CUDA memcopy and not CUDA memcopy async. So the CPU is going to wait. At some point in time, either earlier or now, GPU will start executing these three instructions. Once it gets over and the queue is empty, the stream is empty, that means iteration I equal to 0 is over. At that time, CUDA memcopy is going to return because the copying is over. Okay. So iteration 0 is done. Now the CPU goes back and starts executing iteration 1. Right? This is not required because the second I equal to 1 data is independent of I equal to 0 data. So the iterations are supposed to be parallel with respect to each other, right? And that is going to get ensured only when CPU keeps pushing them into the work queue. If CPU doesn't push, then that is going to be anyway sequential.
Basically, you want to do away with I/O bound of the computer. You want the computation to be I/O bound. You want to asynchronously keep on copying the data and the computation happening because the data is already available. It doesn't have to wait for the I/O from the CPU to the GPU. Is the whole point of this. Basically, the I/O bound part, if the copy was not async, then the whole computation would be I/O bound, right? It would have, like, since the computation is faster than the I/O, or the copying between the CPU to GPU. So that's, I mean, I understand that's an underlying assumption, and we want to keep the data ready for the computation, and given the yeah, that is what I think. That is what I would want to.
Actually, no. So we are currently not concerned about whether it is compute bound or I/O bound, because the computation is not going to begin until the I/O is done for that particular iteration. Similarly, the I/O is not going to begin from GPU to CPU until the computation is over for that iteration. So that sequentiality is anyway maintained because it's stream I for CUDA memcopy async, for K as well as CUDA memcopy async. So anyway, that is sequential. So imagine the case where these are, you don't use any stream here.
Okay.
in that case, how is going to be the behavior? So all of these are going to use the default stream. So there is a default stream which we have been using. So all the iterations are going to go into the same stream. But at least, and therefore, I equal to 0, these three operations, CUDA mem copy, K and CUDA mem copy, these are anyway sequential, but the second iteration is also sequential. I equal to 1 is also sequentially executed.
Okay.
So because of this stream, now different iterations are going into different streams.
Okay. So earlier, so I to just restate it. So what we were trying to do earlier, we were just trying to distribute the computation across CUDA threads, right? Now we are trying to distribute the copy and the computation via streams.
That is correct. Yes, that is correct.
So the parallelism is not just at the computation level as well as the copy level is what we are adding another level of abstraction is what we can understand.
Sure, that is a good way of looking at it.
Okay, thank you, sir. Thank you.
So in case somebody had any question on this, please feel free to ask. Sayan says for the next program, all K1, all K2 and all K3 will be printed together, but overlap among the three clusters. Okay, let's. So we have these three streams, and these K1, K2, K3 are being pushed into totally different queues, and therefore they can get printed in any particular order. Yeah, and all K1s will be together, all K2s will be together, and all K3s will be together. That is correct. Just that the order between them is not clear. So that seems to be fine. Sometimes we would like to synchronize with respect to a stream. We are using multiple streams, but we are interested in whenever a particular stream's functionality is over, I would like to perform some processing, right? So device synchronize is for all the operations of all the streams, right, of that particular device, whereas there is CUDA stream synchronize, which ensures that you can wait for only the commands for that particular stream. Yeah, I'll skip this part. So in general, this asynchronous execution or concurrent execution is good, but it also increases the number of concurrent behaviors, right? So satisfying dependencies becomes the crucial part in the context of whenever you support these streams. So sometimes you need to, for example, you would like to say that whenever you have completed execution of certain number of tasks, I would like to invoke something on the CPU, right? So for example, you might want to say that I'm going to push K1, K2, K3 into the GPU queue, but after K2 is over, I would like to get a signal such that I can execute something on the CPU. Maybe I just want to log something on the CPU. Such kind of operations require something called as a callback, and which is a common concept even on the CPU, just that it is explicitly supported on the GPU, right? So callback is like, let me know when you finish K2's execution so that I can do something, right? So it's similar to sleep and wake up mechanism in the OS kernel. So how do you specify that? Well, we insert a callback inside the stream at the place where you want to get the callback. Okay? So this callback function gets executed on the host after all the previous commands in that queue are executed. And yeah, so there is some issue with respect to the default stream, which I'll skip. And callbacks are blocking, which means that they finish execution and you cannot intercept them. So let's understand this. So where there are multiple streams, right? And for each stream, I'm going to create the stream, and then I'm going to push a kernel into that stream. And for each stream, I'm going to add a callback function. The syntax is in which stream, what function to call back, and then some parameters to be passed and some flags. So I'm going to do a my callback and then CUDA device synchronize. And that is going to, well, CUDA device synchronize is probably not required here, but anyway. So in every stream, I'm going to invoke this K and after that the function my callback should get invoked whenever k is fully over, that is k is fully executed. Okay, so looking at this particular code, can somebody suggest what will be the output of this particular code? I think that 0 is not a flag, 0 is the value that is given. No, I think 0 is the flag. Yeah, II is the value. Okay. So this my callback gets the, yeah, so this data is what this II is. So can somebody tell me what will be the output of this particular code?
So here we are just creating a stream and not copying anything, not doing anything using the stream, right? We are just creating the streams for each kernel computation, and we are not using it for any purpose.
Yeah, we are not copying the data, but that stream can be used even for the computation.
Okay, okay. So
there are, assuming that n is 2 in this case, there are 2 streams, and each stream is running one kernel each, and then there is callback also inserted after the kernel. So accordingly, what will be the output of this particular code is the question. Sowmeya says in kernel k followed by inside callback stream number, right? So in kernel k should get called for first stream, and then inside callback 0, and then in kernel k again for the second one, and inside callback 1. That should be the output of this particular code. Any questions on why we will get this output? Okay. So I'm going to change it a little bit now, right? So I have added this additional call. So there are 2 kernels separated by the callback. Now what will be the output? Okay, Chinmay says interlude print between different kernels is possible. In general possible, not in this example. And why is that? For loop is sequential. Well, that is not the real reason.
the callback is blocking, is it, sir? I think.
Yeah. See, that callback is going to happen at some point in time.
Right, sir.
The question is that okay, let me put it this way. Let me go back to this particular one. So why different case of different I equal to 0 and I equal to 1? Can these 2 kernels execute in parallel? Or another way to say it is that can iteration I equal to 1's printf happen before iteration 0's printf? That is, in kernel k of I equal to 1 happens, and then in kernel k of I equal to 0 happens. Okay, Sandeep says yes. Anybody wants to support or refute Sandeep? Okay. So
It is synchronized within the loop, right?
where is that?
CUDA device synchronized within the loop.
That's right. So there is CUDA device synchronized here, and therefore until the iteration 0 is over, we won't go to the iteration 1. And therefore, in this particular case, you will never, I mean, always in kernel k will be done for I equal to 0, and only after that in kernel k for I equal to 1 will happen. But in general, if that CUDA device synchronized is removed, then it's possible that you can see these different Ks happening in parallel. Right. Okay, so now right. So that's what Sowmeya Lakshmi also said. Okay, so what will be the output of this code? So now in kernel K will be printed 4 times, and you have to decide where that callback is going to be. Okay, any questions on this particular output? Yes, Sandeep.
Sir, here we have CUDA device synchronous right at the end. So I think the first in the iteration 0, the first kernel invocation in kernel, and after that inside callback 0, and in kernel of this same iteration should be done before going to the next iteration because of CUDA device synchronous, I guess. So why wouldn't that did not like in the next iteration it is not the case, like the kernel K got printed before callback 1.
Okay, so that is correct. So that is what I was observing, that whether you guys catch this. Yeah, so this particular thing is not possible, right? Because we expected that the callback must happen between these two. Right, and when we say that callback is blocking, that means that until the callback is over, the next kernel is not taken for execution, or even next item in the queue. So the actual should be exactly the symmetric output should be. Okay, sounds good. Any questions on this one? Okay.
So, but callback is not satisfying the meaning, right? I mean, it should have been like the whole point was callback was some event is happening asynchronously. We just want to know whether the event has completed, right? But here we are trying to say that CUDA stream add callback. This callback is blocking. We are not proceeding to the second instantiation of the kernel invocation until this callback is done. So that is kind of not I mean, usually when we have callback, we say, okay, we on a click or something, right? Whenever click happens, we just call that. But
right, that's right. So the reason why, okay, so I think this is more of how you decide or design this particular callback. So you're right. So typically the callbacks that we have are, in a sense, asynchronous as well as non-blocking, in the sense that that can be invoked as another thread, and the next operations can still proceed. Right? Whereas in this case, by making it blocking, you are not allowing the second in kernel K to get printed. Right? So that is a design decision in CUDA. So you are right that in many other implementations on the CPU, the callbacks are not blocking. Okay. Any other questions here? Message callbacks here are just to add order to the stream. No, the order is already there in the stream. It's more to do with that when, see, CPU is going to just push the elements into the queue, right? All these kernels and different order and so on, right? So all that is pushed into one particular queue. Yeah, no, that order is fixed. But at some point in time, you want to execute a CPU code. See, all these kernels are running on the GPU, but at some point in time, you want to execute a CPU code. For this, the callback is, because the callbacks are happening on the CPU. This my callback function is running on the CPU. So at some point in time, you need to have a way to execute it on the CPU, because CPU has just launched these kernels inside the queue, and it doesn't know when each function is going to get executed. Yes, Sandeep.
Sir, just for confirmation that here you're doing CUDA stream add callback, right? So can I assume that this will block the CPU, and this will the moment this instruction is called, all the elements in the queue should complete, and then this callback will be completed, and after this the queue is empty, or the corresponding stream queue.
No, 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 no. Okay, let's think about it this way. That see this the way kernel is going to get invoked. That is, you are pushing that kernel into that work queue in that stream. Okay, but the kernel might not start immediately. Is this okay?
Yes, sir.
In a similar manner, CUDA stream add callback will add some sort of uh, whatever, some mnemonic into the queue to convey that it needs to get back to the CPU, it needs to stop the processing of the next kernel into the GPU and get back to the host, let it execute the function, and then come back and start executing the next instruction into the queue. So CUDA stream add callback is not going to be synchronous. That is synchronous, meaning it's also going to just add it to the queue and come back and start executing the next instruction, in this case kernel invocation. Right? So all of these are pushed into the queue. Think about it that way, that K, then my callback and K are added to the queue, right? And then the CPU is just waiting at CUDA device synchronous. Okay. At some point, the GPU starts executing element by element from this queue. It sees K first, it executes it. Then it sees, oh, there is a callback to my callback. It informs the CPU that invoke this function. During this time, the CPU was waiting, and maybe as a thread, it is going to invoke that my callback function and signal to the GPU back that my callback is now over. CPU continues to wait at CUDA device synchronize, and GPU was waiting while that my callback was happening. After it receives the signal that my callback is over, then the GPU starts executing the next instance of the kernel. Right? So that is how we should think about it. Yeah, Sandeep, go ahead.
So if we remove the CUDA device synchronize here, and then CPU will be executing and it will not wait, right? So in that case, so when this GPU sees this my callback in its work stream, so then the process control should like the GPU should wait and process control should go to the CPU, right? But the CPU is not waiting actually. CPU is already executing another instruction. Is it that the instruction pointers are pointing like?
No, no, no. So even CUDA device synchronize, when it is waiting, it's actually executing some instruction, right? It's looping. So this gets implemented as a multi-threaded program on the CPU, right? So that CUDA device synchronize is going to wait. Whenever there is a my callback, another thread on the CPU will start executing that my callback.
Okay, sir.
All right. So let me quickly finish about the events. Right. So callbacks are within a stream. K1, callback, K2, all in the same stream. Events can help you communicate across streams. Okay. For example, we can create start-stop events, and we can create the events and destroy them. And there are specific functions which can help us with the synchronization across streams. For example, I can have, let's say, two streams A and B, and then there is one event. I create these streams and I create the event. After that, K1 is invoked into stream A. Oops, sorry. K1 is in stream A. Similarly, K2 is in stream A, and between them is the event in stream A. Okay. So this until this point, it is similar to callbacks, where I have pushed K1, then I have pushed a callback and pushed K2. In this case, it's an event. At some place in time, I want to ensure that before I invoke K3 in stream B, the K1 from stream A should be over. Right? So there is communication happening from K1 to K3. Okay, maybe there is some data which got computed in K1 which you want to be available in K3. In such cases, the events are helpful where you can add, I am waiting for an event from stream B for the event, right? So that event here matches here, and these streams are different, right? So, and in this manner, we ensure that K3 will not execute until K1 is over, or in other words, K3 executes only after K1 is over. K2 and K3 may execute concurrently. Any questions on this particular aspect of the event? All right. So events usually also help us time. So there are specific functions like CUDA event record, so that you can measure the start. So CUDA event record stop, and then CUDA event elapsed time can give you the elapsed time. Of course, you can use other functions like get time of day, but this also helps. Yeah, so one quick part where there might be you want to create a parent stream and there are n child streams, right? The parent stream does preamble and postamble, and then the child kernels actually do the work, right? So n children, each child stream enqueues a kernel work, right? So what we want to ensure is that preamble happens before any of the n works, and postamble happens after all of the n works, right? So if you look at it diagrammatically, it looks like a diamond, where the middle points here are all n works. This is preamble and that is postamble. So you want to ensure this particular dependence diagram gets created. How do you do that? Using events, I would like you to think about. Meanwhile, I'll take this question. Yeah, Sandeep, go ahead. Okay, Sandeep, you are not audible. Okay, Sowmeya Lakshmi says that the call waits for whatever is in the stream when we record the event. Yes, it could be a kernel call, it could be a CUDA mem copy, it could be some other CUDA function. But yes, it will wait for any event, any activity that is happening inside that stream. Okay, so I'll just show you quickly how. Okay, so I had the diagram, I should have shown it directly. Yeah, so that gets, yeah, so it's a little long code, but I'll explain this and then we'll stop. So we create a parent stream, right? And within that, we invoke a preamble in the parent stream, right? So this part is fine, and postamble also gets invoked in the parent stream. So this part is okay. Now, I'm going to record an event which is called parent event. This is the first part. This particular event indicates whether preamble is done or not, because all the children need to wait for this preamble to happen. So each child, each of the n children is going to wait for the event, parent event, in their child stream. Okay? And then only they are going to invoke the work in the child stream. Right? So this dependency from this to this is going to ensure that preamble happens before any of the work happens. And similarly, each of the, so essentially these arrows in the diagram, those many events we have to create. Sorry, not those many events. I should say the starting of those need to be the number of events created, right? So there is one event created for these, and then one event each to be created as the start of each of the bottom arrows. So we create those many events as child event of I in child stream of I, and then wait for that event in the parent stream. Right? And only when all of these are over, then only the postamble happens. Right? So this kind of ensures that all this dependence is met, and in general you can create arbitrary diagrams and ensure that that particular dependency is over. All right, so I'm going to stop here. If there are any further questions, I can take those up. Towards the end, I would also like to say that I mean, this is my I mean, the end of lecturing from my side. Tomorrow, Pradeep is going to tell us more about C++ programming and directly accessing, directly processing the accelerators using C++. But one thing I would like to mention is that this is a semester-long course at IIT Madras, and we have abridged it as, let's say, 4 lectures. And all of you sustained through these lectures. Thanks for that. Also, many of you are doing assignments. That is very good. But beyond this course, if you have any other requirements that comes up as part of your work, research, etc., feel free to get in touch. And there is no problem in asking me questions even otherwise. So feel free to be in touch. Tomorrow at 9 o'clock, again, we'll have a discussion on the assignment A4. And at 9:30, we will have Pradeep's lecture happening, or maybe just before 9:30, assuming that the discussion ends before that. Sandeep, you have a question?
Sir, regarding the assignment 2, sir, can I ask it now?
Yeah, sure, go ahead.
So, actually, I think there is a version problem because I have checked the document of latest version CUDA 12.3. There, the kernel invocation of using the groups or like this cooperative groups has changed. I guess I don't have access to the version which sir was like. There was a command given that I can see that sir is using some 10.2 CUDA version. I think the API has changed. So
Oh, I see.
I think so, but I think that will affect the code which is given for us because I have seen what sir told. I think I have done exactly the same, but even like you told that you can implement your own global barrier, but that is resulting into deadlock. I have tried because the number of blocks is more than what it can do. So the document does not guarantee this.
I see. I
So
see. So it's a different CUDA version that. So you are using CUDA 12, is it?
12.3, yeah, that is the latest. I think, like in the command which Sir gave, it is 10.2, like in the code. So I am assuming that the code is also the same version.
I see. I see. Yeah, that's definitely a possibility. This version mismatch is a big problem currently, and it's possible that it might have changed, and therefore you might be getting a different output. That's quite likely. Maybe you can inform Ashwin over email that this is one possibility. And oh, Ashwin is here. So yeah,
Yes.
Ashwin is using.
So it is in 10.x and but in the document version, it is clearly mentioned that it must uh, it must use CUDA some, there is an API actually.
I
I
see.
don't remember that.
Sure. Thanks for that. Maybe that's the reason why it is not working for some. Sure. All right. So I'm going to stop the recording now. And there are any questions, I'm available. Let me